All right, so here's a very similar problem to the last one that we did. So we have a planet. So this is just a generic planet, and here's our planet right here. Okay, and I labeled it P, and the planet is some distance from its moon, and so here's the moon. There's the distance. I guess I should have put the P a little over. All right, so anyhow, there's the P. All right, so the planet is right in the middle, and the moon is going around. Okay, so the moon. This is the planet. Um, and we it's given. So this is r, the distance. All right, so the r is given to us as 4 times 10 to the fifth. All right, so one just to make sure that everybody knows that this means the same thing is 4 just like a certain scientific calculators, like Texas Instrument calculators, have the E button or the EE button as the times 10. So this 4E5 just that also means 4 times 10 to the fifth, and that's what I was saying right here. And it's in kilometers. Okay, so kilometers. So if I write 4 or 4 times 10 to the fifth, that means the same thing. All right. So just like the last problem, we're going to figure out how fast it's traveling. All right. And they also give us that the this particular moon takes 33.45 days to go all the way around. All right. So the velocity is going to equal the distance divided by the time. All right, so they give us the time. Now, to do this problem correctly, let's put the d has to be in kilometers, right? And the time, even though it's in days right now, let's convert that to hours. All right, so we'll figure out the velocity in kilometers per hour because that's going to be very useful for us in the second part of the problem. All right, notice the second problem, they give us the size of the planet, or the radius anyway of the planet, and it says how much time does it take this moon in the shadow? How much time is this moon in the shadow of its host planet during a lunar eclipse? Remember, a lunar eclipse is when the moon is in the shadow. Of course, remember it could be any planet, all right? So this is just some made up planet, all right, and made up moon for that matter. All right. So anyhow, the circumference, you might recall from the last example, is 2 pi times the radius. All right. So the velocity is, and also the time, the period of time here is given to us as, in this particular case, this moon takes 33.45 days, right, to go day. That's a D. And so let's convert that to hours. So we know that in one day, there are, of course, 24 hours. By the way, the the fact that one day is 24 hours is pretty unique to the Earth. But we use 24 hours as a day, and we're going to always stick with that. All right, so I mean, a day on another planet might be a different amount of time, and that's perfectly fine. We're not talking about how long it takes the planet to rotate at all. We're just using um, Earth units here. All right. So anyhow, the distance cancels, and so we get our scientific calculator, and we're going to figure out the amount of time here. So this is going to be 33.45 times 24. All right. So this is going to be the number. This is going to be the number of hours for the planet, for the moon to go all the way around its planet. So it's 802.8 All right, so let's write that down. So it's going to be 802.8, the decimal point, hours. All right. So now we can continue this problem. And so the distance is, we basically have almost all the information to get the velocity. All right. So the velocity of this particular moon is the distance that it travels, which is, since it's traveling in a circle, and it's approximately a circle. It's actually not technically a circle. It's in what's called an ellipse. We'll learn more about that later when we talk about Kepler's first law of planetary motion. Anyhow, so it's almost a circle, and so the circumference, the distance that it travels, is 2 pi times our radius, which is 4 times 10 to the 5th, all right, or 4e. So this is going to be times 4e5 kilometers. All right, so we've got to put the units there. And then we divide by the time here, which is 802.8 hours. All right, so that's going to give us the velocity in kilometers per hour, and then we'll work on the rest of the problem. All right, so this one has, so we have to figure out how fast the moon is traveling. Here, let's go back to this. All right, so it's going to be 2 times pi. Hopefully you have if you have a scientific calculator, you have a pi button, times. So it's going to be, so this is the scientific part of the calculator. So it's going to be 4, and for this particular calculator, it's this button right here, EXP. Most calculators nowadays, it's an E button, but some of them have an EXP. 4 times 10, see the E times 10 to the 5th. All right, so this, what I'm about to do when I hit equals, that'll be the distance that it travels. All right, so that's the circumference. So it's 2,513,000, blah blah blah. Right? Okay. So we're going to take that and we're going to divide by the number of hours. All right. So the number of hours to complete one orbit all the way around its host planet. All right. So divided by 802.8. All right. So this will give us our velocity. So our velocity is, and so notice what we have here. Let's just keep it to, we'll just round it to, we'll go to the hundredths place, right? Because we had a hundredths place right here. This turned out to be exact, so there could technically be a 0 behind the 8, which I didn't write. But so it's going to be, the velocity is, so that's really important to remember that. This is going to be 3,000. All right, so let's write it down. So it's going to be 3,100, and I already forgot it because the calculator went away. 3,130.64. 30.64. 30.64. 64. That's a 6. And the units, of course, are kilometers per hour. All right, and the reason that I wrote it that way is we want to know how long, the planet casts a shadow, and one of the things that we're going to assume is the shadow is the same size as the diameter of the planet. All right, so knowing this velocity and knowing this equation right here, okay, so this equation right here, we're going to reuse this equation, and we'll figure out if we know the velocity and the distance, we can rearrange this equation and solve for time. So that's really now this is going to be the time that the moon is in the shadow. All right, so I'm going to draw a picture. All right, so we know that the planet had a radius. All So I'm going to use a different R for the radius of the planet, or R sub P for the radius of the planet, was 6,700 kilometers. All right, so this is going to be our distance, but remember it's in that's the radius of the planet. All right, so that's R sub P. That's the radius of the planet, and so we want to know what the diameter of the planet, which of course would just be twice that. Right, so the diameter of the planet, I'll call it D sub P, for diameter of the planet, is going to be 2 times 6,700. All right, kilometers. So that's the distance, and what we can do is we take the equation V is equal to D. In this case, it's going to be D sub P, the distance, and the velocity, of course, is the velocity of the moon, which we've already calculated, divided by T. All right, so in general, velocity is distance divided by time. But we're using this in a slightly different way. We're wondering, how long would it take the moon to cross the diameter of the planet, all right? Because that's approximately the size of its shadow. All right, so if we rearrange this equation and solve for time, you get time. So I'm going to put the time on this side of the equation. Time is going to be multiplied by the velocity of the moon, and would just be equal to the diameter of the planet. And then, of course, just to finalize it, I'm going to divide both sides by the velocity of the moon. Right, divided by the velocity of the moon. Right, the velocity of the moon cancels on this side, and so that pretty much finalizes our equation. The time. This is the time, and we're going to want the time to be in hours, is going to be the diameter of our planet, which is twice its radius, so it's 2 times 6,700 kilometers, all right, kilometers, divided by the velocity. Let's see, let me look again just to remember what that number was. I wrote it's in my calculator. Hopefully still. Yeah. So, and we rounded it to 2 places past it. So it's 3,130.64. 3,130.64. And notice the units were kilometers per hour, right? And so the kilometers cancel, and you'll have 1 over hours, and the hours will come up to the numerator. All right, so we're about to figure this out. All right, so let's go back to this. So the let's get the calculator. Show the calculator. Let me scoot that over just a little bit. All right, so since I already have this number in my calculator, I'm just going to say. I'm going to put that in storage for just a second. Well, I don't have to put it in storage. It's a pretty small number. Anyhow, here, let me put it in storage just for the heck of it. All right, so it's going to be 2 times the radius of the planet, so that's 6,700. So this is the diameter that it's traveling. All right, so 13,400 kilometers, and it's doing that in a time at a velocity of 3,130.64. All right, so I'm going to divide by divided by 3130.64. Right, I rounded it to the hundredths place because I started with something in the hundredths place. All right, that was the best that we knew, and so this is going to give us the number of hours that the moon would be in the shadow of the planet when there's an eclipse. So since we went 2 places past the decimal before, we're going to report it 2 places past the decimal again. So it's going to be 4.28 hours.